Let's discuss about the concept of calculation of force on side walls of a random-shaped vessel. Let us first discuss about the typical vessel, which we usually use. Say we are given with a conical bucket, in which we fill up the water. And in this situation we know well that this water, due to its weight, will push the bottom in downward direction and will push the side walls in the direction normal to the surface. Obviously, due to its reaction, the bottom will apply a normal reaction on the fluid body, say N1 in upward direction, and N2 in the direction normal to the side walls of the vessel. So in this situation we can say overall weight of this water is balanced by one is N1, other is the vertical component of the force exerted by side walls, as the horizontal component of the force exerted by side walls will always cancel out as the fluid is in equilibrium. So in this situation, say we are required to find this N, which is the force exerted by side walls. Then for this N, horizontal component will get cancel out and only component which will be exerting force on liquid is NV, that is the vertical component of the force applied by the side walls on the fluid. So for its calculation we can directly state, if we calculate pressure at bottom, if h is the height up to which the liquid is filled, this pressure at bottom can be simply written as h rho g, which is due to the weight of liquid. And if we find out, say we are also given with area at this bottom, which is say A, so we can find out the force acting on the bottom of container is, this force can be directly written as h rho g multiplied by the area. And this is basically the normal reaction N1 which the bottom is exerting on fluid. And in this situation, we can directly state the weight of this liquid is more than this normal reaction, as it is balanced by the side walls also. So we can directly state in this situation, if we draw the free body diagram of fluid body, then it can be written that for this fluid body its weight mg is acting in downward direction. If m is the mass of fluid taken in the bucket, and in upward direction it'll be experiencing 1 is the N1, the normal reaction due to the bottom, and other is NV, which is the vertical component of the force exerted by side walls, as the horizontal component is already balanced. So in this situation we can directly write for equilibrium of fluid body. Here we can write N1 plus NV is balancing the weight of this whole liquid. So this NV, which is actually the force exerted by side walls on the fluid body, can be written as mg minus N1, of which the value we already calculated as h rho g into A, which is the force exerted by fluid pressure on bottom. So this is the way how we calculate the force acting on the side wall. Here the sides walls are exerting force on the liquid in upward direction. But actually it depends on the shape of surface. Let's see few more situation in which we take different kind of vessels which are exerting force by the side walls in different directions also. Let us discuss few more situation, like, say we are given with a vessel of such a shape in which the top is circular, and the side walls are given like this, and the bottom is having a cross-sectional area A. In this situation, if it is filled with liquid, we can see in this situation the liquid is pushing the side walls normal to the surface, and side walls are exerting a force in the liquid in opposite direction. So below the middle height you can say the side walls will exert a force on the liquid in a direction normal to the surface, and always we can say the horizontal components will be balanced out, and vertical components will be left over. But you can simply state The side walls which are above the middle height will be pushing the fluid in downward direction, due to the shape. And these are having vertical component in downward direction. So in this situation we can simply state, if we draw the free body diagram of the fluid weight mg will act in downward direction due to the normal reaction N1, which is acting at the bottom. N1 will act in upward direction. Now in this situation in the container, if weight is more than the normal reaction N1, then obviously in this situation this NV will act in upward direction. But in some situation, we'll also take some example. In some situation, if N1 is more than the weight of the fluid which is contained in the vessel, in that case NV will act in downward direction for the equilibrium. So we can simply state, for equilibrium of fluid we'll always write the similar situation N1 plus NV is equal to mg. So NV can be written as mg minus N1, and N1 can be calculated by multiplying fluid pressure at the bottom with the total area of the bottom. Say if we consider a situation in which we are given with a vessel like this, in which a very small opening is there at the top of the vessel and the bottom is closed by a circular base. And say if in this vessel a liquid is filled. Here in this situation we can say if the base area is A. Here we can see the bottom will be exerting a normal reaction in upward direction, and all the side walls will be exerting the force on fluid in inward direction like this which I am drawing. And again the horizontal component of all these forces will cancel and vertical component will exist only in downward direction. So if we draw the free body diagram of this fluid body, mg will act in downward direction here, N1 will act in upward direction, and obviously here NV will be acting in downward direction because in this situation the normal reaction applied by the bottom on the fluid body is more than the weight. That's why for its equilibrium in this situation, N1 must be equal to mg plus NV. So here, the force exerted by side walls on the fluid which always in vertical direction, and here it is in vertically downward direction, can be given as N1 minus mg. And as usual, if h is the height up to which the liquid is filled, N1 can be written as h rho g multiplied by A. This is the way how we calculate the force exerted by the fluid on side walls, or force exerted by side walls on the fluid. It is vice versa in opposite direction.